How's everyone who's watching this? This is my 30th video on the channel, and today we're going to begin our 4th book, Intensive Science and Visual Philosophy by Manuel DeLanda. In my eyes, this is a great introduction to Deleuze, and by extension Guattari's, ontological project, even if it's a bit science and maths heavy. To give something of an outline for the book, DeLanda's focus here is primarily on Deleuze's schema of the virtual, actual, and intensive, using his concepts of multiplicities, developed in 1,000 Plateaus and, under the name Ideas, Difference and Repetition, as a guidepost. He takes these notions and applies them to the philosophy of science, bridging the gap between continental and analytic theory. Without further ado, the first chapter is titled The Mathematics of the Virtual, and concerns just that, developing a mathematical definition of multiplicities, and setting down what DeLanda calls a state-space ontology. Because of its length, I'm going to split it across 2 videos, with the second part hopefully coming out not too long after this one. DeLanda starts off the chapter by pointing out the importance and enduring nature of multiplicities in Deleuze's philosophy, stating that
this concept makes its appearance in his early books and remains one of central importance, with an almost unchanged meaning and function until his final work.
To understand this longevity, it is crucial to grasp why it was developed in the first place. Basically, multiplicities are Deleuze's response to the problem of identity, acting as a replacement for essences, those irreducible properties that make a thing, well, a thing. Although DeLanda doesn't really elaborate too much on what he means by essences here, I feel that some background on this notion will be very helpful as we get into the more technical side of multiplicities. To put it simply, from an essentialist point of view, objects in the world are nothing more than the deformed representations of some transcendent, idealized thing. Take a drawing of a cat, for instance. For the essentialist, it has an identity only in its relationship with the perfect abstract idea of a cat. Based on this cat essence, we can construct what is known as a natural kind, a collection of entities that all represent it, and thus resemble each other. Every cat, fictional or not, is a member of this natural kind, all just flawed representations of the perfect idea. In contrast to this way of viewing ontology, which is focused on identity and representation, Deleuze turns his attention towards morphogenesis, the processes that give rise to natural kinds in the first place. Whilst the essentialist may look at a cat and declare it so based on its relationship with an essence that transcends both time and place, a morphogenetic approach will instead look to how that cat came to be in the first place. What historical processes were involved? How did evolution lead to that specific form? In this way, DeLanda argues,
while an essentialist account of species is basically static, a morphogenetic account is inherently dynamic.
Another important distinction to make here is that morphogenetic accounts are immanent, in the sense that they don't draw from some abstract realm of archetypes, or what have you. Everything is taken from the world itself, and the form-generating resources that make it up. With this out of the way, we can get into multiplicities proper. As a starter, when it comes to the maths of a virtual, there are 3 main fields that the concept takes from: differential geometry, dynamical systems theory, and group theory. It's around these that DeLanda structures most of the rest of this chapter. He starts off with an exploration of differential geometry, giving a bit of a background on the field. Essentially, it was developed as mathematicians, in particular Friedrich Gauss and Bernhard Riemann, found that differential calculus could be applied to geometry. This form of calculus is used to study the rates of change of quantities relative to other quantities, like in the case of velocity, where it can be determined by measuring spatial change in relation to time passing. Differential geometry expanded on this by applying it to curvature and other similar properties of shapes, making it possible to measure infinitesimally small points with the rates of change alone. So, how does this relate to multiplicities? Multiplicities are closely connected to this calculus-informed variety of geometry, having entered Deleuze's lexicon as a translation for what is usually termed a manifold in English. Setting the groundwork for this mathematical concept was Gauss, in his work on surfaces. Essentially, he discovered that it was possible to use rate of change in order to find the curvature of 2D objects without placing them in a 3D embedding space. In other words, he was able to study surfaces locally, without having to compare them to outside bearings. In effect, Gauss was able to treat surfaces as spaces in their own right, defined completely intrinsically, or to put it in more Deleuzian terms, immanently. Manifolds took form as Riemann applied this notion of intrinsic definition to n-dimensional spaces, basically structures with a variable number of dimensions, be it 4 or 100. Both these features also define multiplicities, on which Deleuze states,
multiplicity must not designate a combination of the many and the one, but rather an organization belonging to the many, as such which has no need of the unity in order to form a system.
Unlike essences, which exist in a transcendent embedding space, multiplicities are, just like manifolds, defined completely immanently. There is no outside force imposing itself from without, just the multiplicity itself. At this point, DeLanda says that it could be objected that this is simply a matter of semantics. As such, something else has to be introduced. It's here that dynamical systems theory comes in. Manifolds are used in the field as a way of conceptualizing physical processes, like that of a pendulum swinging, or of a bicycle going down the street. When it comes to constructing a manifold in dynamical systems theory, you start by figuring out how many degrees of freedom a certain thing has. In other words, how many ways can it be changed? From this, what DeLanda calls a state space can be developed. Each degree of freedom becomes a dimension, every point the object goes through being mapped onto it. To give a concrete example, let's look at pendulums. When it comes to swinging one, there are 2 degrees of freedom, velocity and momentum. As such, a manifold mapping it has 2 dimensions. As time goes on, it's possible to note down on each dimension how the object's degrees of freedom change. Maybe velocity decreases, for instance. From this, it's possible to construct a trajectory, the final result being the capturing of a process. The same thing can be applied to bicycles, which have 5 main parts: the handlebars, front and back wheels, 2 pedals. Each of these parts has 2 degrees of freedom each, again being velocity and momentum. When we model the processes connected to its movement, we are thus left with a 10-dimensional state space. The purpose of this is twofold. On the one hand, it makes it easier to map complex dynamical processes as trajectories. On the other hand, conceptualizing these processes in terms of space allows us to draw from topology in order to explain recurring behaviors. It's here that DeLanda introduces singularities, a concept developed by French mathematician Henri Poincaré that Deleuze makes central in his ontology. Put simply, these refer to attractors, points on a manifold that organize the behavior of trajectories that fall into what is known as the basins of attraction. When not under the influence of any other forces, trajectories that enter into a singularity's basin of attraction will ultimately end up at a specific point, as seen in this diagram. Because of this feature, singularities can be thought of as the long-term tendencies of a system. Trajectories often don't start at the singularity, but instead, essentially by accident, eventually fall into its basin. At this point, DeLanda differentiates between 2 different kinds of singularity, describing the first by saying,
Some singularities are points, so the final state they define as the destiny for the trajectories is a steady state.
This type of singularity, referred to by DeLanda as a point attractor, is stable, involving a single endpoint. For example, the momentum and velocity of a pendulum always tends towards 0, equilibrium, without fail. However, this isn't the only variety of attractor. In DeLanda's words,
Poincaré found that certain closed loops acted as attractors and called them limit cycles.
These singularities are oscillating, meaning that trajectories waver between multiple points, rather than just one stable one. As a little aside, a word that DeLanda will use throughout this book to explain such a singularity is periodic attractor, periodic in the sense of being oscillating. To give a concrete example, the orbit of a planet is maintained by a periodic attractor, since instead of endlessly moving towards one singular point, it rather moves cyclically through a number of different states. Moving on, DeLanda seeks to show how singularities, as what structure multiplicities, can explain the genesis or creation of physical forms. He begins with the example of a soap bubble and a crystal of salt. For both, the singularity that gives rise to their form is a point of minimal energy. Minimizing surface tension results in a bubble. Minimizing bonding energy results in a cube-shaped crystal. Thus, in Deleuze's words,
singularities are implicit forms that are topological rather than geometric.
To give a very simplified rundown on what this distinction means, topology concerns the qualitative exploration of spaces, basically what is unchanging in them, whilst geometry focuses on quantities, distances, lengths, heights, and so on. The minimal point of energy is topological, a quality of a state space, whilst its actualizations in the bubble of a salt crystal are geometric, with measurable curvatures and edges. In this way, singularities have what is known as mechanism independence. They aren't mirrored by their realizations, hence how the same singularity can give rise to two completely different things. Already, it's apparent that these properties of multiplicities are opposed to essences, where, for the latter, the focus is on the idea of perfect geometric shapes that lend themselves to being represented in the sphere of a bubble or the cube of a crystal. However, DeLanda says that we need to make at least a couple more formal distinctions between the two, starting with that of how they are specified. To use his words,
While essences are traditionally regarded as possessing a clear and distinct nature, multiplicities are, by design, obscure and distinct.
This is because, whilst essences can be clearly and distinctly imagined in the mind of a philosopher who considers them, multiplicities are instead composed of sets of singularities that only gradually make themselves known. We can see this with the metaphor of embryogenesis, the development of an egg. From the viewpoint of essentialism, every part of the egg comes into being essentially pre-formed. There is a clear structure organizing every tissue and organ of the animal it contains. However, in actuality, eggs don't work like this. Instead, differentiated structures appear progressively, unfurling as time goes on. There is, in fact, a distinct structure, organized as it is by certain chemical gradients or positions, but it's obscure. In other words, there isn't just some blueprint around which the egg develops. Now, it's important to note that this is only a metaphor. To formally define this characteristic of multiplicities, we need to look at group theory, a subfield of abstract algebra that deals with, as the name suggests, special kinds of sets known as groups. As can be seen in this diagram, groups are composed of a set of some sort, certain properties like closure, and a defined rule of combination. This last term simply refers to things like addition, subtraction, division, etc. A rule of combination simply describes how elements in a set can be combined or changed. When it comes to closure, this is the defining feature of groups. Essentially, as DeLanda states,
When we use the rule to combine any two entities in the set, the result is an entity also belonging to the set.
We can see this by using positive integers as an example. Taking addition as a rule of combination, they form a group. This is because adding two positive integers will simply result in another positive integer. It wouldn't be a group if, for example, subtraction was the rule, since something like 1 minus 5 results in a negative integer. In other words, something that isn't a part of a set. However, Deleuze wasn't really all that concerned with groups of stable objects. He was a process philosopher after all. Instead, to explain progressive differentiation, we need to look elsewhere, that is, towards groups of transformations. As an example, DeLanda offers that
The set consisting of rotations by 90 degrees, that is, a set containing rotations by 0, 90, 180, 270 degrees, forms a group since any two consecutive rotations produce a rotation also in the group.
This is useful for understanding multiplicities because it allows us to think of geometric figures in terms of invariance, unchanging features basically. A better group to use here would be one dealing with 45-degree angles. Whenever such a transformation is applied to a sphere, nothing changes, it remains invariant. However, applying the same transformation to a cube leaves us with something very different. We go from a flat side to a corner. We are able to calculate what's known as a degree of symmetry by taking a figure and seeing how many ways it can be thus changed through the transformations of a given group. In the case of the sphere and the cube, we can therefore say that the former has more symmetry than the latter. The reason why this matters to us is that it allows for the idea of symmetry-breaking transformations. Essentially, transformations that change a given object's degree of symmetry. So, for instance, we can picture a possible process that takes a sphere and turns it into a cube by diminishing how invariant it is. Although it might not seem immediately clear how this relates to physical phenomena, just take phase shifts, where something moves from one state of matter to another, like water transforming into ice or vapor. In much the same vein, taking us out of the realm of metaphor, the unfurling of the egg can be considered in terms of a complicated cascade of these symmetry-breaking transformations. When it comes to singularities, this phenomenon is termed bifurcation, and can be studied by adding control parameters to a state space. To borrow DeLanda's words,
these determine the strength of external shocks or perturbations to which the system being modeled may be subject.
A point attractor, the usually stable variety of singularity, may bifurcate and turn into two when under external forces, forming a periodic attractor. Likewise, such a periodic attractor, when under extreme conditions, might become so unstable that it bifurcates into what is known as a chaotic attractor, where the trajectory's approach is completely unpredictable. A wonderful example of just what a cascade of bifurcations might look like when actualized comes to us in the form of hydrodynamic flow patterns, divided up into three stages of conduction, convection, and turbulence. The first is organized around a simple point attractor, with what DeLanda describes as a rather bland, featureless overall pattern. However, once the system reaches a specific temperature, a bifurcation takes place, and the point attractor breaks down into a periodic one. Convection takes hold, and rolls of water begin moving, either clockwise or counterclockwise, oscillating from point to point. Eventually, though, at an even more extreme temperature, turbulence predominates, the periodic attractor, organizing convection, bifurcating into chaos. At this point, we're left with a cascade that can be diagrammed like so, each bifurcation leading into the next. However, and this is crucial, this hydrodynamic cascade looks nothing like the mechanism-independent model it actualizes. This is because of cause and effect, which doesn't impact the latter, but does the former. For example, in the bifurcation that gives rise to convection, there's a very specific sequence of events that leads up to that point, linked to the interplay between viscosity and density gradients. In the case of Deleuze, the same distinction is important for understanding multiplicities. Whilst they themselves are mechanism-independent, their actualizations are not. Whilst perhaps contradictory upon first glance, this is why they are called concrete universals. To explain, multiplicities are universal in the sense that they aren't restricted to specific conditions, like those imposed by cause and effect. It's thus that the same concrete set of singularities can give rise to multiple highly divergent forms, like the soap bubble and the salt crystal. These divergent forms are also useful for distinguishing them from essences, which are by their very nature general, in the sense that they work through similarities in representation. Everything is related back to the notion of a perfect ideal, natural kinds being the result. A lack of resemblance is a core aspect of multiplicities, which first and foremost give form to processes, not to final products. Having now looked at progressive differentiation, there's one final distinction left to make.
Unlike essences, which as abstract general entities coexist side by side, sharply distinguished from one another, concrete universals must be thought as meshed together into a continuum.
Basically, multiplicities blend together, forming what Deleuze calls zones of imperceptibility, where it isn't clear where one ends and another begins. To quote Difference and Repetition, this is because
they are made and unmade according to the conditions that determine their fluent synthesis. They combine the greatest power of being differentiated with an inability to be differentiated.
It's a very small typographical distinction, but it's important to separate differentiation, with a T, from differentiation, with a C, although DeLanda regrettably doesn't see the need to himself. Basically, the first refers to the progressive unfolding of bifurcations, whilst the second concerns how the continuous space of multiplicities is actualized into the world as we live it. To end this video is differentiation that we'll focus on, seeing how space can be progressively made to be discontinuous. The key concept is that there are two main types of spaces, metric and non-metric. The former refers to those with things like measurable heights, lengths, volumes, and whatever else. However, as the latter suggests, there are some spaces that don't have these things. It's here that DeLanda begins to develop a hierarchy of geometries. Basically, the form of geometry we're most familiar with in our day-to-day lives is what is known as Euclidean geometry, which is highly metric. However, there are more types out there. Namely, DeLanda invokes topological, differential, projective, and affine varieties to explain differentiation. Using group theory, we can explore the relationship between them all. Working in reverse order and returning first to Euclidean geometry, its metric construction allows for lengths, angles, and shapes to remain unchanged when rotated, translated, or reflected. These are called the group of rigid transformations. When we get to affine geometry, it's still metric, but the lengths of the lines aren't really important. A group of so-called linear transformations keeps the straightness of lines and parallelisms constant or invariant, whilst distance itself is left forgotten. Next, projective geometry takes the groups from affine and Euclidean geometry and adds the conveniently named group of projective transformations. These allow for shapes to be equivalent even if parallel lines are distorted. A step above this, at least as outlined by DeLanda, is good old differential geometry, which in turn is followed by topology. As we discussed earlier, topology deals with the qualitative study of space. In other words, it's non-metric. No matter how much you stretch or meddle with it, messing with the lengths, angles, and so on, a topological figure will remain the same. Hence the common joke that topologists can't tell the difference between donuts and coffee mugs, since the one can be deformed into the other. Having outlined these different geometries, we can get to work constructing a hierarchy of differentiation. Each way of looking at space has its own degrees of symmetry, Euclidean being the least symmetrical and topology being the most, as seen in this diagram. It's thus that we can move from one to the other through bifurcations or symmetry-breaking transformations, where topology is differentiated into differential geometry, which in turn differentiates itself into projective geometry, and so on, until finally a metric result is found in our Euclidean world. Explaining this concept, I think it would be best to use DeLanda's own words.
The hierarchy, topological, differential, projective, affine, Euclidean, may be seen as representing an abstract scenario for the birth of real space.
Essentially, there is originally nothing more than a topological continuum. However, as it gets increasingly differentiated and loses symmetry, the space goes from non-metric to metric, giving rise to distinct, discrete forms, our lived reality. To help visualize this, a diagram might be helpful. Although unfortunately I couldn't find an example from differential geometry, all of these shapes are equivalent, some simply having frameworks that offer more symmetry than others. Although the topological figure looks and, well, is a sphere, it can be molded into a cube without any of its properties changing due to the logic of its space. The same is true for projective and affine geometry, although with less symmetry-maintaining transformations available to them. To give this metaphor some ontological significance, it would be useful to now look at what Deleuze means when he talks about intensive and extensive properties. As you may remember from science class, extensive properties refer to those that can intrinsically be divided, designating things like length, area, and volume, along with energy and entropy. What this means is that they can be broken down cleanly, with differences in degree. As DeLanda says,
if we divide a volume of matter into two equal halves, we end up with the two volumes, each half the extent of the original one.
These are contrasted with intensive properties, which basically refer to those things, such as temperature or pressure, that can't be divided in this way. The example he gives is of trying to divide the temperature of 90-degree water. Splitting it into two halves won't leave you with a couple containers at 45 degrees each, just two instances of the same 90 degrees. In Deleuze's work, these types of properties are what ultimately give rise to extensive features. To use an example that DeLanda doesn't offer, hurricanes are a great case study in this regard. They're composed of a myriad of intensive forces, like pressure, velocity, and temperature, which, as they cause them to form, give way to measurable extensive quantities, like height, momentum, and what have you. Going back to the topic of differentiation, the metaphor of different geometries can thus be replaced with the idea of an intensive space, one composed only of continuous intensive properties, that undergoes a cascade of bifurcations that results in the genesis of discontinuous extensive forms. It's on this that I'd like to end, being essentially the crux of DeLanda's argument thus far. Now, this concludes the first half of Chapter 1 from Manuel DeLanda's book, Intensive Science and Visual Philosophy. I truly hope you enjoyed or learned something, and if you feel I got anything wrong or wasn't as clear as I could have been, please do feel free to let me know in the comments so I can do better. Next time, we'll finish the chapter and examine some of the logical implications of Deleuze's ontology. Until then, bye!